So hello everyone. I want to introduce Cinthia Huerta Alderete, and she's going to talk to us about quantum walks and Dirac cellular automata on a programmable trapped ion quantum computer. Cinthia, take it away.
Thank you so much. Today I'll be talking about quantum walks in trapped ions. This is a project that is related to my PhD and is basically related to some quantum physics simulations in trapped ions. So first, I'm going to talk about a little bit quantum walks, and the basic idea of this is thinking in the classical case. We have we have two. We have a walker in our system, and the position of a walker is going to be defined for the result of a coin. If this coin is a classical coin, then a walker can perform steps into the right or into the left based in the result of this coin. The final distribution for this kind of classical random walk is going to be like the distribution in the gray color. But if our coin is a quantum coin, then our walker can perform steps into the left and into the right at the same time, having as a result a final distribution that looks like the blue one, where is less likely to find the walker in the original position. Quantum walks has been gained a lot of interest in the community. We have, in the past 2 years, there was a proper seminar only for quantum walks. There are many applications for quantum walks that are related to quantum search, isomorphism graphs, and physics simulations. And regarding to physics simulations, in this talk, I want to talk about the simulation of the Dirac equation by using quantum walks in a trapped ion system. There are many platforms where quantum walks has been realized that are related to nuclear magnetic resonance, trapped ions. Other experiments in trapped ions have been done where the position is mapped into the phase space. And also there are some other experiments in optical lattices, but here we are interested in do circuit implementation of quantum walks in our system. This is a picture of how our system looks like. In the figure on the right, we have some side views of our trap. This is a pole trap, and this view is giving us an axial confinement. And in the picture of the left, we can see some segment place that is going to provide the axial confinement of our ions. So it's here where we can trap a small change of ions. The ion that we are choosing is ytterbium 171. And here I am presenting the level structure for ytterbium 171 that looks like complicated, but we need to pay attention to these lower states, whereas is here where we are identifying our computational state. This state has a quality that it has a magnetic field number equals to 0, which means our qubit is going to be insensitive to changes in the magnetic field. Another thing that we should pay attention is to this transition, because in this transition we can use it to do Doppler cooling, to initialize our ions, and to do detection of the quantum state of our qubits. To initialize, we use optical pumping, which basically means that we send light to this particular frequency, and very quickly we pump to the zero state. in order to do the detection of the state at the end of the simulation or any computation that we are doing, we also we need some kind of dependent measurement, so we can generate a state dependent measurement that basically means that we are going to send light also at this transition, and this is going to cause a scattering of the photons into the bright or state one, and then we can count the fluorescence after a certain amount of time. With this, we can describe some sort of statistics for our ions. If we have 0 counts, then that means that our qubit states or remains in the dark state, and if we have like a number of counts in our system, then that means that our ion is in the bright or one state. We can do these measurements with high fidelity. This is the fidelity for our states is in the 0 and 1 state. Another ingredient that we need is how to manipulate our qubits, and to do that we use a Raman scheme, which basically means that we send a pulse laser that is split into 2 halves, and the difference between those 2 halves is related to the splitting of the qubit. Those two halves basically are shifting with respect to each other. Then that means that we can address the qubit by using this transition. This is like a big picture of our trap. Here in the middle, those blue dots are the qubits that we can trap, and those purple lines are related to the Raman beams that we are using to address the ions. One of them is illuminating the entire chain, and the other one is coming from the other side, and is going to be split into several channels in such a way that each beam can illuminate each ion individually. That means that we have individual addressing, and we can control the phase, the frequency, and the amplitude for each qubit. To image or for the readout, we have an object system that is going to send light to this multiplier tube, and in such a way that we can in such a way that in this multiplier tube, each ion is going to be related to a different channel here, so we can detect the fluorescence of each ion. This is like the image that we have from the PMT. In this axis we have the channel, and each channel is going to be associated to each individual ion, and in the vertical axis we have the number of counts for each ion, so we can tell if the ion is in the bright or dark state. And the native operations that we have in our system are related to single qubit rotations and 2 qubit rotations. The first one is easy to implement. Basically, what we do is just to turn on our laser in resonance, and then we can get some kind of gravity flow for each of the individual ions. So basically, we can decide the axis where our qubit is rotating, and by the angle also we can say like how much is rotating respect to the axis. So this is how we describe our general single qubit rotation, but also we have single qubit rotations in the z-axis that is done without errors. For the two qubit rotation, basically here we have the carrier, that this is the one that we use to perform Rabi flow for the single qubit rotations. And if we detune by motional frequency of the trap, we can change the spin of the qubit and add or subtract some motional quantum to the system. So if we have only one ion, then we have three frequencies here that is going to be related to the carrier and the two sidebands. If we have more ions, then we are going to have as many sidebands as the ions. So here in particular, I'm showing two of the modes of our system when we have 5 ions, and we can use those to perform an entangling gate. This is how it looks like the unitary for our entangling gate. And basically, we can change the angle for this rotation continuously. And that is going to allow us to perform some entangling rotations. Here, during an entangling operation, all the ions are participating, but only the ones that has the beam on are the ones that are going to rotate. So then that means that in our system, we can perform any pair of entangled rotations, which means we have full connectivity, and we can use this to implement any kind of quantum algorithm. So until here, I have described some of the layers that we need to compile and execute a quantum algorithm. The first part that is related to the hardware is what I already told you about the system that we have. And in order to describe some sort of another quantum operations, we use the two native gates that we have in the system that are XX gates and single qubit rotations. So for example, we can create an operation that looks like this, a C-swap, where basically the state of this qubit is going to change based in the state of the first qubit. If this is 1, then those two are going to flip. In order to implement this kind of gate in our system, we need to use single qubit, the two qubit, the two native gates that we have in our system. That basically what is important here is that we are going to have some single qubit rotations, but some angle and also some two qubit rotations. So in our system, we have a sort of table where our system can look at when we call these kind of operations, and our system is just going to perform all of these operations. So with this, this experiment was done in the past in our system, and this is exactly the same truth table that we saw the slides before. So with this in mind, we want to do some implementation of quantum walks in our system. As we said before, there are two main ingredients for quantum walks. That one is the wildcard, and the second one is the coin operation. There are two flavors for quantum walks. One is related to the discrete time quantum walk, and the other one is related to the continuous time quantum walk. For the experimentals that we did in this project, is only related to quantum walks in a line, discrete quantum walks in a line. the position of worker is, or of the position of worker or particle is gonna be related to certain number of qubits, and we are gonna take the last qubit to describe the coin in our system. So the evolution of the system is going to be described for these operations, where we need to look at the result of the coin, and based in this result, or worker or particle is going to move. So at the end, we should be able to recover a probability that looks like this. The coin operation is going to be related to some single qubit rotations, and the question now is how to describe the step evolution for the system. So in our experiments, we want to realize experiments in a 5-qubit system. One of the qubits is going to be related to the coin, and the rest is going to be related to the position of the system. We can think naively, and we can say that each qubit is going to represent a different position for the worker. But if we do that, then the number of operations that we need to perform only a few steps is going to grow faster. And what we want to do is some sort of kind of optimize the resources that we have to perform our quantum work. So instead of doing this, we are going to choose a mapping where we use the qubit basis to describe the position. This is the particular mapping that we are using. So if our particle is in the zero state, we need to perform some operations to move to the new plus or minus one in the position space. The circuit that we are implementing to perform our quantum work looks like this. And basically each dash box is going to be one step. For each step, we are going to start with a coin operation, and based in this result, we are going to move our particle backward or forward. But here we still have some operations that requires a large number of gates. So what we are going to do is try to optimize first those blocks of gates. So as in our system, we can perform any of the usual computational gates, and also our 2-qubit gate, we can perform it with any angle. So then that means that we can perform CNOT gates and all the roots of CNOT gates, in particular the square root of CNOT gate. So if we do this identification, we can reduce the number of 2-qubit gates that we need to optimize the number of gates that we need for each state. So basically what we are doing is 2 steps optimization. The first one is by looking at the definition of the TOEFL or TOEFL 4 in terms of the square root of the CNOT gate, and then translate those gates to our native qubits in such a way that we can reduce the number of the counting number of gates that we need. In particular, after 5 steps, we only need to perform 32 2-qubit rotations in our system. The implementation of this circuit in our system looks like this. On the left, I have the simulation, and on the right, I have the experimental result. So we did this experiment with different coins, where the coin is in 0, 1, or in a superposition of those states. So when it's 0, we can perform a walk to the left. When it's 1, we can perform a walk into the right. And when we have a superposition in the coin, we can perform a symmetric quantum walk. From here, we can see like the experiment agrees with the simulation, and we can distinguish very well the left or right what that we wanna do. So we're going to use these ideas to perform some quantum physics simulations related to the Dirac equation. In order to do that, we can use a split step evolution where basically now we are going to have 2 coins, and each coin is going to tell us if we move into the left or right in our quantum walk. So if we have if we know the distribution of our particle at some time t, then we can infer the distribution at some time t plus 1 by applying this new step evolution operation. If we do that, then we recover some distribution for the particle that moves into the left or right. But from here, what is important is that we can just associate the information of the particle moving into the left or moving into the right. We can summarize those 2 evolutions into a differential equation. And by doing some assumptions here, we can describe the massless Dirac equation or the massive Dirac equation. And again, we can just use the previous circuit that I showed before, but now we want to change the coin operations for each other step. And until here, we may be wonder how adequate is this description of the Dirac equation. In order to realize that, we make a direct comparison with the analytical solution provided by Strauss, that is the blue line here. And we took the probability distribution that we found after each position, after each step. So after 3 steps, and after 3 and 5 steps, we can see that the distribution that we recover with these quantum circuits match with the solution provided by Strauss in 2006. Here, the yellow lines corresponds to the probability of time after 3 and 5 steps, and the blue line is analytical solution. Here, the mass is going to be related to the value of the angle for our second coin. And again, in terms of the experiment, we change the mass of the particle, and if our particle is if the mass of the particle is really small, then we can find this bimodal distribution that Strauss showed before, and we can see how this distribution spreads out after each step when the mass increases. So we can see how the particle takes longer to describe that bimodal distributions that we saw before. So until here, we keep some sort of basis for the description of quantum walks in our system, and we provide some experimental results for quantum walks with different coins. We use the same scheme to simulate the Dirac equation in 1 dimension, and here for us it's important to choose an adequate mapping, because this mapping is going to allow us to optimize the resources that we have available in the system, which basically means reduce the number of gates that we need to perform any particular state. And just by choosing an adequate mapping, and by increasing the number of qubits available in the system, we can implement more states and also perform some other quantum physics simulations. So thank you so much, and I would like to thank you to the people in my lab, in the Link lab, and also to our collaborator, to our theory collaborator. Thank you.
Let me start by clapping. Thank you, Cinthia. So Let me check the Slack if there's any questions. There's some clapping, of course. So I'll give them a minute to post some questions. I see Ross is typing something. Question. I think you said this, but how deep was each layer in the end? Ross asks.
Here, sorry. After each sorry. In the table that I present for the first qubit, for the first step, we have around 8 gates. 5 of them are single qubit rotations and only two qubit gates. And the number of gates is going to increase after each layer. So after 5 steps, we have 20 single qubit gates. And sorry, we need to add all of them. So after 5 steps, we have 32 2-qubit gates and around 80 single qubit gates.
I'm guessing Ross would be more interested in the 2-qubit gate count because they are more expensive practically.
Yeah.
Would you agree?
Yeah, that's true. So for the first step, we have 2. For the second one, we have 6, and then 10, and then 21 and 32.
Thank you. Ross says in the end, meaning after optimization. That's great.
Yeah, this count is after optimization. If we want to count before optimization, for each CNOT gate, we need 5 operations. For a TOEFL gate, we need 11. 5 of them are 2-qubit gates. And for a TOEFL gate, the original implementation that we have in the lab, for a TOEFL gate, we need an ancilla. But if we describe first the TOEFL gate in terms of the TOEFL 4 in terms of a TOEFL gate and CNOT gate, we can get rid of the ancilla qubit.
And yes, and Melf Johansen asks a generic question about ion traps. How do you think the number of qubits / ions in this area will develop in the future? Just a guess.
Yeah. People is still pushing hard to increase the number of qubits in the system. For us, the number of qubits is quite small, but there are some other groups where are increasing this number. For example, just at UMD, there are some other experiments that they are working with 30 or 50 qubits.
You mean with ion traps?
Yeah, with ions.
Okay, wow, good to know. Ross is typing something. I'll give him some seconds. Ross, type faster. I'm generally interested in the translation from gates to laser control. Can you say more about that? Not a real question, sorry.
Yeah. So I don't know what is happening. Yep. Basically, we have 3 frequencies here in this slide. the carrier frequency and the sidebands. So for single qubit rotations, we perform Rabi flops at resonance, which means at the carrier frequency, and we need to look um, at the duration, for example, just to know which angle we are rotating the qubit. And we use the sidebands to perform 2-qubit operations. And basically, this means that when we set bichromatic bit knot with the Raman laser, we can detune, or we can excite simultaneously the red and blue sideband. That is the one that is going to give us this change in the spin and the motional mode at the same time. So basically, we are going to excite the motional mode during this operation in order to add or subtract a quantum motional in the system, and this is going to allow us to change the state of the spin. So this essentially what we are doing is to perform a Momer-Sorensen gate in our system.
Thank you very much. Okay, I think you've answered all of the questions, and we're almost out. Well, we are out of time. So thank you again for the talk. Let's clap again, and feel free to roam around in the Slack and chat with the audience for more Q&A. Thank you.
Thank you.